Brings us to the final presentation before lunch, which is a presentation also from DTU, brought to you by Amos Schledorn, and this is about optimal scheduling and electricity market participation in district heating under uncertainty.
Yes, thank you very much. So I'll be talking about production optimization and electricity market bidding for district heating systems, which I'll do mainly along two papers, one of which was main authored by our colleague Daniela, and the other one was main authored by myself. So the motivation of why we're doing this is to minimize the operational cost for district heating systems, which is both a good idea for the district heating system operators, but also for customers, because it reduces their heating bills. One aspect that often gets overlooked, but that becomes pretty apparent when you talk to district heating system operators, is automation of what they're doing. So even if our models perform just as well as what district heating operators would do manually right now, they would very much appreciate if we take away some of the manual labor they do by automating kind of typing things in the computer. And finally, we believe that intelligent system operation, especially when district heating systems are coupled to the electricity system, finally supports the integration of renewable energy. So this is just an example output of what our model would spit out. This shows the production schedule for a district heating system across 2 weeks, and it shows the heat output of different production units. Here we have two biomass boilers, CHP units, and 2 gas boilers, and the dashed line shows storage operation. So this is my sales slide, the features. So what we can do right now is we're able to represent arbitrary energy carriers and arbitrary network structures. We are also able to account for various forms of uncertainty. We believe that operating district heating systems is inherently subject to uncertainty. For example, uncertainty in electricity prices, in waste heat generation, in heat demand, etc. We're also able to do day-ahead market bidding, which I'll talk more about later. What we can't do right now is intraday and balancing market bidding. We'll only do that in a couple of papers very rudimentarily. We are kind of able to represent different temperatures and flow rates in the form that we're able to represent arbitrary energy carriers. So we could represent conversion from one temperature or from one flow rate to another, but we don't do any temperature optimization or hydraulic modeling per se. So this is how we represent district heating systems. It's a directed graph where every node in the system stands for some kind of energy source or energy sink or conversion or storage of energy in some form. And then we can transport energy through the system by propagating through the graph. We kind of extend this graph by adding a temporal dimension. So the graph kind of grows in a temporal dimension, and this is how we're able to represent dynamics of the system. So basically, you can imagine this as making a copy of this graph that then represents the state of the system at different time steps. We represent uncertainty via stochastic programming, and stochastic programming assumes uncertainty to be distributed across discrete distribution. So we kind of add another dimension to this graph by saying, well, we have a state of the system across different scenarios, and those scenarios are connected in the graph. So in the end, this all is not different graphs, but it's one very large graph. And the good thing is that this is extremely generic, because we found out that basically all the systems that we worked with have their own quirks and their own individual features, and we really needed a model that can capture all of that. We've applied that model across 3 different case studies in Denmark, one in the city of Middelfart and Fyn, one in Brønderslev and one in Hillerød. I won't talk about these systems in great detail because that would take too much time. This is the simplest of the systems, the system of Middelfart. Here we have energy sources on the left-hand side, which are biomass and natural gas entering the systems. Those get converted in CHP units and in gas boilers, and they serve energy in the form of electricity and heat. The other systems are a little more complicated. So, for example, in Brønderslev, we also have solar heat, which is highly stochastic. We have both electricity consumers and electricity producers. And in Hillerød, we have yet another system that is a little more complicated. So this is the other sales slide where I tell you how good our model is. This shows the value of the stochastic solution. That's a metric which measures how good our stochastic model performs in comparison to a deterministic model. I'm showing this here for different seasons for the different models. In the case of assuming no particular bidding, meaning that the district heating systems are just price takers, we can see mild improvements on average, and very large improvements in one case in June 2021 for the Brønderslev system. What gets quite apparent is if we add electricity market bidding, again in a simple form through the construction of bidding curves, we see that this gap kind of increases because this bidding method is very much tailored towards stochastic programming. That brings me to the second part of my presentation, which is more about power market bidding. So power market bidding for district heating systems is typically based on what we call unit switching prices. Here I'm plotting the power price on the x-axis and net heat production cost on the y-axis for a CHP unit and for a gas or biomass boiler. And what we can see is that while the net heat production costs for the CHP unit naturally decrease with a higher power price because electricity sales generate more revenues at higher prices, the cost for the boiler would stay constant. And at some point, those costs intersect. And this intersection point we call the unit switching price. And since that price kind of corresponds to that power price at which the district heating system operator would be willing to switch from the boiler to the combined heat and power unit, vice versa for electricity consumers, sensible bidding prices must somewhat correspond to those unit switching prices. And this helps us a lot because then we can kind of narrow down the possible bidding prices for the system. Another problem we incurred is that heat producers are typically subject to startup costs and to minimum up and down times of the units, which means that typical hourly bids are not really an option because it's very inefficient to be scheduled for 1 hour because a bid was won in one particular hour, but not be scheduled for the next hour and then again be scheduled for the next hour. So we work with block bids, which are either fully accepted or fully rejected over the bidding period. But that kind of adds another level of complexity because you could submit the same bid in different forms. So here I'm showing for 2 CHP units, and the bid on the left-hand side could either be submitted as one long bid at a lower price where we distribute the startup cost over a longer time frame, or we could have 2 shorter bids at shorter time frames where the startup costs are distributed over a shorter time frame, thus generating higher bidding prices. We've solved this in a mixed integer linear program, and for the system of Middelfart, which is the simplest of the 3, without great surprises, to be honest. So we can see that the average heat costs, which are depicted here in the top row, those are higher for the colder months as expected, And bidding intensity also increases for the colder months because CHP units compete with biomass boilers in the system, and they get scheduled more and more if the heat demand is higher. Yes, so to conclude, we're doing production scheduling for generic district heating systems. We're able to represent arbitrary energy carriers, arbitrary network structures. We do so under uncertainty in order to incorporate uncertainty in the form of stochastic prices, stochastic solar heat, etc. We're able to do day-ahead market bidding to account for startup costs. And our next step is kind of the combination of this graph-based model that I presented in the beginning and the block bidding model that I presented secondly. Yes, thank you very much.
Thank you. Any questions?
Okay, so you talk about this electricity market bidding and talk about two types of electricity market can be bid. So for your case, do you consider both separately, or actually you can consider the two types of electricity market at the same time?
Which types of electricity markets?
You're talking about this intraday market and the day-ahead market, right?
Yes, at the moment we're not doing intraday or balancing market bidding. Balancing market bidding because it's very difficult to forecast balancing prices. So you could do some kind of rudimentary bidding in the sense that whatever excess capacity you have, you bid it at whatever price. And intraday market bidding is then even more complicated because it doesn't follow the same rules as day-ahead market bidding and balancing market bidding. So at the same, right now we're only doing day-ahead market bidding.
Thank you. Maybe it slipped my attention, but do you have any buffer capacity in your simulation here? I mean, years ago we were working on optimizing energy systems for greenhouse growers, and they typically had a CHP and they have a buffer tank, and they also, you know, have can do some electrical heating, and I mean they have a lot of mix. So I was just wondering here, when you show with your CHP, I was thinking, do you have the opportunity to have some, I mean, pre-storage of heat?
Yes, so all those systems, I would guess every district heating system in Denmark has a large storage capacity. For example, for the case of Middelfart that I talked about, we have 2 storage units. It's a little hard to see here. They're called S1 and S2. So typically those systems are almost have overcapacity. This is why we can kind of do this bidding based on saying we could either produce heat without market-dependent units or with market-dependent units.
More questions? Well, maybe one, it's not a question, it's more a remark, just to give some context also for the people who are not, I mean, for the people doing research in electricity rather than in heating. I think this is very important research for a future energy system, because in countries like Denmark, but also in Germany, you see more and more that there's an excess of renewable electricity often. You have wind power and you just have to get rid of it. And what happens nowadays that often those windmills are just shut down because they can't use the power when it's available. And by by using this kind of market-based production techniques for district heating, you can use the flexibility that there is in heat networks to absorb this excess of electricity and other way around when there's a lag to switch on CHPs. So I think this is something that you will see more and more in the research, and that the research that we do, power grids and heating networks, will come together more and more.
Yeah, I think it often gets overlooked that storing energy in the form of heat is orders of magnitude cheaper than storing it in the form of electricity, and especially in a country like Denmark, where you have a cold climate, the flexibility potential of district heating is just immense.
That's correct. So that's a nice conclusion, I think.